Let's think about how energy conservation links to the work-energy theorem. If you have been following this video series, you will have noticed a few times where I have shown that you can transform the work-energy theorem into energy conservation, and therefore you can go backwards as well. Let's look at this a little bit more and also give an example. So firstly, depending on how you define the system, you can either use the work-energy theorem or conservation of energy. Because if you define your system so that the work done by external forces is zero, then you can just use conservation of energy. If, however, you define your system so that the work done by external forces is non-zero, then you are forced to use the work-energy theorem. It gets a little deeper than that, though. And let's take a look. Mathematically, to go from work-energy theorem to the conservation of energy, what you're doing is you're taking a term and moving it from the left-hand side to the right-hand side. So for an example, consider a system where the only work done is by conservative forces, there are no dissipative forces. The work-energy theorem reduces to our good old-fashioned work-kinetic energy theorem. So we have the work done by conservative forces is going to be equal to the change in kinetic energy of our system. Well, as you know, the work done by conservative forces is also equal to minus the change in potential energy. And so we'll have minus the change in potential energy is equal to the change in kinetic energy. We can then add the change in potential energy to the right-hand side, and we end up with the final equation, 0 equals change in kinetic energy plus change in potential energy. So mathematically, what we did is we took a work term on the left-hand side of the equation and then turned it into an energy term and pushed it to the right-hand side of the equation. So that's all that this amounts to mathematically. To go from work-energy theorem to conservation of energy, you're just moving a term from the left-hand side to the right-hand side, or vice versa. Because of how easy it is to transform between energy conservation and work-energy theorem, you might then ask, how do I know which one to use when? Well, as with most problem-solving strategies in physics, use whatever is practical, whatever makes your life easier, whatever you are able to do based on the information you are given. It's possible, and in many cases in introductory physics classes it is the case, that you can use either one, in which case just use whichever you prefer. One possibility that might help you determine things is that it's not always easy to change the work term on the left-hand side of the equation into a potential energy or internal energy term that you can move to the right-hand side of the equation. We could do it in this case because we know the work done by conservative forces is equal to minus the change in potential energy. But what if you have non-conservative forces? Well, if they're dissipative forces, you know that you can change that into change in thermal energy, change in internal energy. But if there are other non-conservative forces, you may be stuck. And so you'll have to leave it on the left-hand side of the equation and leave your equation as the work-energy theorem and solve the problem that way. Let's look at an example now. Let's consider an object falling under the influence of gravity down an incline, and we'll assume that the incline has friction on it. Well, one way we can solve this problem for whatever information we are interested in is by the work-energy theorem. And so what we can do is we can write down the work done by gravity plus the work done by friction is equal to the change in kinetic energy of our mass, assuming that we define our system to be the mass only, so that these two are outside our system. Of course, we don't have to do that. We can have them be internal forces, and the work will still be equal to the change in kinetic energy. But as discussed in previous videos, it's usually easier to think about the work being done by external forces when you're using the work-energy theorem, as opposed to the energy conservation theorem, where it's easier to think about the work being done by internal forces. Unless, of course, you have those non-conservative external forces that we've talked about before. But anyway, that's why I'm doing what I'm doing here. All right, so this is one way to treat this matter. But we also know that the work done by gravity, that's a conservative force. We could instead write that as minus mgh, right? Or just to leave this a little bit more general, I'll call it minus change in potential energy due to gravity. Well, we can move this over to the right-hand side, and then instead we have the work done by friction is equal to the change in kinetic energy plus the change in gravitational potential energy. So this would be equivalent to redefining our system. Of course, as I just noted, you don't have to do that, but just using the conventions that I have recommended using. We redefine our system to be the mass plus the Earth as well. But we ignore the surface of the incline. In that case, then, we have changes of energy inside our system, and we have the work done by friction as an external force, changing the energy of our system, of the mass plus the Earth. Of course, we know the work done by friction, we can rewrite that as the change in thermal energy or internal energy. Well, once again, we have this change in energy term. Looks kind of like a potential energy because it's minus, and we can move it over to the right-hand side. If you're wondering where the minus sign comes from, it's because the work done by friction, remember, is going to be negative because it's going in the opposite direction of the movement. And as a result, you're going to end up with a minus sign on this side. Or if you don't buy that argument, then remember when we talked about the work done by friction, it was the same as having no friction and adding a thermal energy term on the right-hand side. Since I have it on the left-hand side and I need all this to be consistent, I have it with a negative sign instead. However you want to slice and dice it, you're going to get the work done by friction is equal to minus the change in thermal energy of our system. It is removing energy from our system. But if we instead include the incline inside our system, we can once again move this over to the right-hand side of the equation. And then we will get conservation of energy once again. It's possible that we could have had another external force, maybe somebody pushing the block as well, in which case now we would have an extra term here, a work push. If we happen to know what that work push did in terms of change of energy of the system, if we had some function for it, like we did for friction and for conservative forces, we can move it to the right-hand side as well, and we would once again get energy conservation. We can go backwards, of course. I can bring this to the left-hand side, I can bring that to the left-hand side, and go back to our work energy theorem instead. And so you see then how the work energy theorem and energy conservation relate to each other by moving terms over from a work term on the left-hand side to an energy term on the right-hand side.